Sulfate ion. We are going to predict the correct Lewis dot structure using formal charge computation repeatedly for this one. Sulfate ion is composed of one sulfur atom, four, as you can see here, four oxygen atoms, and it has an excess negative charge of 2. So that means it has an excess electron of 2. So sulfur is a group 6 element. Also oxygen is a group 6 element. It has both has 6 valence electrons that are involved in bonding. And there is an additional 2 electrons that is involved in bonding for this ion, sulfate. Now this is the orbital notation for sulfur. The electronic configuration for neon plus this one. So there are 6 electrons in the outer energy level, level 3. So remember that in level 3 is capable of having another orbital, the d orbitals. Okay, so if it takes 2 electrons, it will now satisfy the octet rule. It is now stable. Same for oxygen. The helium electronic configuration plus the 2s2 orbital and 2p4 orbital. So again, if it takes 2 electrons, if it has 2 electrons shared with it, it will now be stable. It will now obey the octet rule. It means that there will be, all of the orbitals will be paired. So we are now going to choose the central atom, the one with the lower electronegativity is the central atom. So for sulfur 2.5, oxygen 3.5, our central atom is sulfur. So with sulfur as our central atom, we are going to propose a Lewis dot structure. Now this one, there's plenty of possible Lewis dot structure here, and you will see all of it. And then we're going to place it with a small picture of each. Okay, so now stare at the screen, and I'm going to show you each of the possible Lewis dot structure for sulfate. And let's not forget the excess 2 electrons here, because it's a charge species. Okay, now let's not forget the available electrons. 6, 6, 6, that is 18. 7, 7, for a total of 32 electrons. Alright, now, so I just rearrange it. Okay, so as you can see, there's 32 electrons here. Okay, 6 here, 2 of each are in forming a lone pair. Also here, lone pair, single bond, single bond, single bond. So this is just one of the possible Lewis dot structure for sulfate. The total electrons here is 32. You can pause and count the number of electrons. Okay, so don't forget. So what's happening here is that this 6 electrons here belongs to oxygen. 1, 2, 3, 4, 5, 6. The one that is inside the circle came from sulfur. So in case you're confused about how the electrons were moved in this figure. Okay, so 6 from this oxygen, 6 from this sulfur. You know, initially we have a drawing that sulfur has 6 electrons. Now for this oxygen, it has 6 electrons. We added an extra electron here. So this is just for purpose of illustration. We're going in drawing. We are trying to derive the correct Lewis dot structure for sulfate. Next, we can have a structure with a double bond. So what we did is we took the lone pair, place it here. So we can also do something like, so here, 1 double bond and 3 single bond. We can also try to have 2 oxygen forming 2 double bonds with the central atom sulfur. The next, we can have like 3 already there, or all of this forming a double bond. So which one is the correct structure? So all of those proposed Lewis dot structure are written here, are shown here. So to know, to find out the correct Lewis dot structure, we're going to use formal charge computation. The formula for formal charge is group number minus the summation of number of single bonds and number of unshared electrons. The best way to memorize this is the group number of the element minus the summation of lines plus dots. Okay, so let's try first with this figure. Sulfur here, okay, so don't forget sulfur and oxygen are both group 6 elements. So here sulfur has 4 lines associated with it, 0 dots. So what we're going to do is the flow here is clockwise. Okay, this oxygen followed by this oxygen followed by this oxygen followed by this oxygen. So I already prepared it that way. So this oxygen, group 6 element, 1 line, 6 dots. The same with this oxygen, this one is for this oxygen. So here's the summary of it. Positive 2 minus 1 minus 1 minus 1 minus 1. What is the summation of this? Negative 2, which is the same as, so the summation of formal charge for each component should be the same as the charge of the polyatomic ion. So 2 minus 1 minus 1 minus 1 minus 1, negative 2. So how about the second drawing? Group 6 element, 5 lines. This oxygen has this formal charge. This oxygen, this formal charge. This oxygen, this formal charge. And then the last oxygen, group 6 element, 2 lines, 4 dots. So unshared electron, because although this is a lone pair, it is not shared with any other element. So 1, 2, these 2 dots. It is an unshared electron. It is not shared with another element. It belongs to oxygen. So 1 minus 1 minus 1 minus 1 is negative 2, still same as the charge of the ion. Now for the third drawing, you already see how this goes. Group 6 element, 6 lines. This one pertains to this oxygen. Okay. Third oxygen, this one. Fourth oxygen, this one. Okay, and the summary, we place it here. The fourth drawing, sulfur. Now there's 7 lines associated with our central atom. This oxygen, 0 formal charge. This oxygen, 0 formal charge. This oxygen, negative 1 formal charge. This oxygen, 0 formal charge. The summary written here. The last one, sulfur, 6 minus 8, negative 2. This oxygen, this oxygen, this oxygen, this oxygen. Okay. Sulfur is least, what's the value written? 2.5. Okay. So sulfur is least electronegative compared to oxygen, 3.5. So 2.5, 3.5. So that means this is not good because the negative charge should be, as much as possible, belong to the more electronegative element, oxygen. So we cross this out as one of our choice. Also this one, the negative charge, and it's 2, right? It's negative 2. The negative charge should belong to the more electronegative element, oxygen. So these 2 structures, we don't choose it. Okay? And we choose, so that's quick, we choose the one at the center. Why? Why not these 2? First of all, although it's good that it has a positive charge for sulfur, 0 for sulfur here, as much as possible, each of these components should be near 0. The one that has the components in terms of formal charge computation near to 0 the one that has many atoms with formal charge near to zero, is more stable. Okay, compared to this one, as you can see, the formal charge, if there's one double bond, the formal charge of this oxygen is -1, sulfur +1, while this one, only 2 oxygen has a formal charge. The rest are neutral, 0. So this is better compared to this one. So the structure for sulfate is that sulfur has a single bond. So for this 4 oxygen, sulfur forms a single bond with 2 oxygen and double bond with the rest of the remaining 2 oxygen. Okay, so we'll choose this structure. Electron groups. So electron groups, we count a single bond, double bond, lone pair equally. And we're talking here about the central atom, sulfur. So sulfur has 2 single bonds and 2 double bonds. So the steric number, or the electron group, for the central atom here is 4. 1, 2, 3, 4. Now, what is the importance of getting the electron group? We determine the electron group because it is associated with how the atoms are arranged in space. Okay. So these electron groups, electrons are negatively charged particles. They repel each other. So as much as possible, they will have a separation in space that minimizes that repulsion. Okay. So what is the best separation in space? For a polyatomic ion, for a molecule with 4 electron groups, the best configuration is that of a tetrahedral. Molecular geometry is associated with the number of atoms connected to our central atom. Both electronic geometry and molecular geometry are tetrahedral. So both electronic geometry and molecular geometry talks about the arrangement in space. Now let's talk about how bonding occurs. Tetrahedral molecules are said to be sp3 hybridized. This is about the central atom. So the central atom is said to be sp3 hybridized. This is the orbital notation for sulfur. When you say sp3 hybridized, 1s orbital and 3p orbitals should be half-filled to accommodate a sigma bond or a head-on overlap with each of the atoms it is bonded with. Okay, so how are we going to have 3 half-filled orbitals here? So remember that sulfur, its last electrons belong to the 3rd energy level. So it is capable of opening, so 3rd energy level, it is capable of opening the d orbitals. So these 2 electrons can jump here to the d orbitals. Okay, so it can jump there, so that these 4 electrons are involved in sigma bonds, head-on overlap, while these 2 electrons, alright, so sp3 hybridized, that is the meaning of sp3 hybridized, sp3, and then these 2 electrons, unhybridized electrons, are involved in pi bonds. So these 4 sigma bonds hybridize. So this hybridized orbital, the electrons here are involved in sigma bonds. The electrons in this unhybridized orbitals are involved in pi bonds that forms the double bonds with these 2 oxygen atoms. Alright, so there you go. Thank you for watching. Bye-bye.